Okay, so hi everyone. My name is Derek Shank, and I'm from Notre Dame. So thank you for having me, and yeah, so get right into it. So my goal of this project is to find chemodynamically tagged groups, and to do this, we will create a sample using GALA to probe the chemical evolution and galactic structure of the Milky Way. And then eventually we can associate these CDTGs that we find with chemically peculiar stars. In this case, we're going to look at our process enhanced stars and possibly carbon enhanced metal poor stars as well. And then later we could use this as some type of list to find high resolution follow-ups as targets. So in order to get into this, we need to know how the substructure works in the Milky Way. So we're going to go from the most spatially coherent to the least. So on the left here, as we can see, there's dwarf galaxies and globular clusters. These are pretty easy to pick out in surveys just because they are position oriented and you can just look up on the sky and see that they are some type of structure in the Milky Way. And then next is the stellar streams, which are a little bit more disrupted into the Milky Way system, but they do have indicators such as their proper motions that indicate some type of coherent structure. And then finally, we have accretive substructures, which are just randomly distributed throughout the Milky Way. And they don't really have a lot of ways, at least through proper motions or positions, to detect how they are related to each other. So these are what I focus on in my research. And in order to do this, we will need the sample, which is obviously GALAH DR3 data. So GALAH, from my project, is pretty important just because it has abundance information for stars in the sample. Specifically, we look at our process enhancement abundances. So this includes barium, strontium, and europium, and yttrium in our case as well. So we get about 1,000 stellar spectra that meet our requirements of being R process enhanced, which just means that the europium is abundance is greater than 0.3, and the barium to europium ratio is less than 0 to make sure that it's not as process dominated, but rather R process dominated. And then we also have some literature sources that are available that we can throw into the GALAH data set that are not already in GALAH. So then the next step is to cross-match this with GAIA, which I'm sure most of you are pretty familiar with at this point. So there's the EDR3 that came out in December of last year. And so we can use these for things such as the proper motions of the stars and the parallaxes as well to get distance values. And then GALAH provides the radial velocity values. GAIA does as well, but not all stars in GAIA have radial velocity values. So we also use the GALAH radial velocity values. So we can use these astrometric parameters to determine the orbits of the stars. And to do this, we can use AGAMA, which is just an orbit integration software that'll calculate out the orbits of the stars and provide things such as the energies, the velocities, the positions, and the actions. And then using these orbital kinematics that we get from AGAMA, we can create the CDTGs from this algorithm called HDBSCAN. So it's a clustering algorithm that is nice because it doesn't look at the data in any underlying model, and it just clusters it according to its algorithm without assuming anything about the data. So we look at this in the energy and cylindrical action space in order to make our clusters. And then after we get our clusters, we do a galactic structure association through a process in NIDU et al. 2020. And this just compares a bunch of substructures in the Milky Way to what we found in our orbital groups. So this would be substructures such as the GAIA sausage Enceladus, the metal weak thick disk, Thamnos, Helmy streams, stuff like that. And then we can also make past C and DTG associations with the groups that we find in order to see how they compare to past work. And then also we can look at globular clusters in the Milky Way and dwarf galaxies to see if any of these are related as well. So whenever we get it all together, we get 116 CDTGs from GALAH and the literature sample as well. And these range from 3 to 16 stellar members Most of it is 3, but some of the CDTGs do increase in size as you get stars that are clumped together in the energy and action space. So then next step is to match the Milky Way structure. So we have 55 of these that belong to the GAIA sausage Enceladus structure, and then 3 belonging to Thamnos, and then 1 finally belongs to the Helmi stream. So here's an example of what a CDTG would look like for our result. As you can see, you have the structure up top here. It's unassigned for this current one. And then we have some stellar associations from some past work. So there was 2 stellar associations with CDTG 29 from Gooden et al. 2021. And luckily, they both fell in the group 29 for each of them, which means that we have some type of consistency. But there is no group association with that. So our group did not match their group, even though we did have 2 stars in there. And this just could be due to multiple reasons, such as one of the parameters fell out, or the group is so large that it sort of overwhelmed the other group. And then we do have a globular cluster association with this NGC 6293. So that's kind of cool because globular clusters have an indication of how these stars formed or could have formed. And then also we can look at this table and we can look at the elemental abundances, which is why GALAH is so important, such as the europium. As you can see, even though all of these stars are our process enhanced by definition of our sample, we do end up getting a europium to abundance ratio that is 0.439 and has a pretty small scatter of 0.187. And you can look at the other ones as well. And then the metallicity on the far left, as you can see, it's a pretty, well, just a metal poor group. It's not very metal poor, extremely metal poor, anything like that. Yeah, so then in the future, more work that we have to do. We can study the composition of the CDTGs. So look at the europium abundances and the barium abundances and figure out how they correspond to the different substructures that we have in globular clusters and past work and all that stuff. And then we can also get the components and compare them with the substructure as well. So how the different energies and actions compare and stuff like that. And then we can also try different algorithms besides HDBSCAN, such as Stargo and others, possibly StreamFinder if our data set allows that as well. So yeah, that's my project. Any questions?
Well, thank you so much, Derek, for a great talk. We have time for questions. If you're on Zoom, you could please raise your hand or feel free to put questions in the chat. And if you're in the room and you have a question, please find a way to get my attention. Any questions? I have a question while folks are thinking. So one sort of challenge sometimes with working with clustering algorithms, of course, is determining like the optimal number of clusters. Can you comment a little bit about how you made those decisions? Yeah, so HDBSCAN is nice because it doesn't really have any type of clustering methods that you would say, okay, we want like 100 some clusters or whatever. You give it some type of parameter that you tell it, okay, I want to have a minimum number of clusters or a minimum number of members in a cluster. So in our case, it's 3. So you just say, okay, if there's anything less than 3 stars in a cluster, then just discard it. So it automatically just does that for you, which is nice. And one of the reasons why it's preferred over other methods such as friend to friends, where you have to choose a linking variable, and then it makes that hard because you could optimize your linking length variable in order to choose, you know, good clusters, whatever good means. So this kind of takes the guesswork out of it, which is always good. Cool, thank you. So I see that Jeffrey Simpson has raised his hand, which I wonder if that means there's a question in the room.
I was going to say something. I was going to comment about the carbon and just say that carbon in GALAH is an awkward element in the sense we don't measure it that well, especially on the giant branch, there's problems with it. So I'd be wary of carbon abundances. Okay, yeah, that's good to know. Just quickly looking over this, it looks like there's no
carbon for any of the GALA stars. So the GALA stars in this sample have the GALA IDs, and then
okay.
the other stars are the literature ones. So at least preliminarily, it looks like GALA doesn't have any carbon for this sample.
Okay.
And I also don't think we pull carbon from GALA, now that I remember.
It's just Spen's nodding away. I can see Spen nodding away, because one of the things you encounter is, especially on the giant branch, we only can measure the really carbon-rich stars, and so you might come up with a fake result of thinking, oh, all these stars have large carbon abundances. It's just because we can only measure them when they have large carbon abundances.
Okay, yeah, no, that's good to know, though.
Cool, thank you. So we also have a question in the chat from Sarah Martel saying that she likes that you're looking at possible associations with the literature, and she wants to know, how did you compile all of that information?
So it's basically been about a 6-month project where I just read through some literature and then tried to collect as much stuff as possible. And obviously it might not be complete, but to the best of my knowledge it is. And then I just went through each of their data sets and had to gather all the relevant information. In this case, we wanted the energies and actions of different clusters that formed. And then sometimes I would have to email the people who wrote the paper and then try to get information from them, because not all the time was the information complete. So yeah, it was a long journey, but hopefully I'm at least closer to the finished product now, even if it's not always 100% done.
Very exciting, very exciting. Cool. All right, well, thank you so much, Derek. Let's thank Derek again.